Hello everyone. Welcome back to Palance AI and welcome back to the Deep Learning Foundation series. In the previous video, we talked about CNNs or convolutional neural networks and why they are so much better than the dense layer for image classification. In this video, we are going one level deeper and understand the actual convolution operation itself, which is again the foundations for CNN architecture. We'll walk through the convolution operation step by step. For example, how a small filter slides over an image, what is padding, what is strides, and how all this fits together in making CNNs that much more powerful for images. Once you understand convolutions, the rest of the computer vision, the CNN architecture, modern image models, or even vision transformers, at least at an intuitive level, will start to make a lot more sense. If you're completely new to this series, I strongly recommend starting with the earlier CNN Intuition video. I have linked the playlist in the description below. All right, let's break down convolutions visually and also intuitively. Let's jump in. Let me give you a very simple example. So let's take a 2D grayscale image with only 6 by 6 pixels, just to understand how the convolutional operation works. Okay. So let's say these are some hypothetical pixel values. 6 by 6 pixels. Okay. So now I'm going to use a filter, like a window, as I talked about. So I'm going to take this filter. Ideally, this filter has weights, right? But for our sake of understanding, I'm just putting some numbers here. Okay. So you take this filter and you scroll this filter over this 6 by 6 input pixel image. Okay. What does scrolling means? You put it there. Okay. You put on one side, right? And then you do element-wise multiplication of each value of the filter with the corresponding, position in the input image. Okay. So what this means is, like, for example, 0 into 1, right? And then you sum up. So you do element-wise operation of each value of the filter with the corresponding portion in the input image, and you sum all it up. When you do that, what will happen? You'll get one scalar value, and that's gonna populate your new output shape here. Okay, so one operation, one convolutional operation with a filter or the corresponding portion in the input image is going to give you one scalar value. Now what we're going to do is we're going to slide this. We're going to slide this window, just one contiguous window. Okay, so we're just going to slide it a little bit. Okay, now you do the convolutional operation again. So now it's 0.5 times 1 plus 0.2 times 1 plus 0.2 times 1 and plus 1 times 0 and so on. You got the idea, right? You can calculate it just for your cementing your understanding. So that's the convolutional operation. Now you're going to get the second value here. And similarly, you can slide the window a little bit more and then do the convolutional operation again. I know it's 0.1, so you put the 0.1 there. You got the idea. So now contiguously, keep sliding this window, keep sliding. As you do that, what's going to happen? All the values in this output shape gets populated. Bottom line, what happened was when you convoluted the original input image with this 3 by 3 filter, the 6 by 6 original input image became, the final output became, a 4 by 4 image. The image size decreased a little bit. But see, in the process, what you did is, even though you're doing this element-wise multiplication, summing it up for the convolution, in essence, what it's doing is, intuition-wise, it's trying to come up and identify the original input image. It captured some other kinds of particular patterns. What are these patterns? Well, depending upon the values of your filter, each filter, like whatever the values you choose for the filter, right, the output image will look different. So who's going to choose these values for the filter? Well, that's the beauty of deep learning. We don't even have to choose anything. Just for the sake of explanation here, I'm showing you some values in this filter, 1, 0, minus 1. In reality, we just say to our deep learning model in Keras, hey, use this filter 3 by 3 filter. And when we do that, it automatically guesses some weights. And as part of the training process, even the weights of the filter are calculated. We don't have to choose anything. That feels like magic. Okay, when you slide a filter over an input image, right, it typically reduces the image input shape, but bottom line, it's trying to capture a particular type of features or patterns in the input image. Okay, depending upon the values of the filter. So if we use different types of filter, imagine you'll get different types of 2D output shapes, right? Okay. That's what I'm going to show you now. So now let's take an actual input image, okay, which is, let's say, 28 by 28 pixel. Again, this take the pullover image, okay. So this is 28 by 28 pixel image. So imagine all kinds of pixels being populated this grid. Okay, I did not put the numbers there because it would be too hard to see. So 28 by 28 pixels. So again, let's take the 3 by 3 filter. Okay, so you take the 3 by 3 filter. Imagine, right? You take the 3 by 3 filter, you put it on one corner, and once you put the 3 by 3 filter, put it on one corner and slide throughout this entire 2D shape. You did the convolutional operation, right? So as you put this 2D with the filter at one place, you're going to get one value. But as you keep on sliding the entire input image, you're going to get a new final 2D output shape, right? That's what you're going to get. So for single filter, you're going to get one output shape like you see here on the top, the blue one. So you're going to get a new 2D shape with each filter. As you convolute the original input image with the filter, with this 3 by 3 filter, you're going to get a new 2D output shape. But if you have, let's say, 10 filters, each filter is going to be scrolled over this input image, right? Scrolled over, or once it does the convolutional operation, it's going to create a new output shape. In essence, each filter is capturing a particular types of patterns in the original input image and outputting a 2D output shape. So basically, if you use 10 filters, right, again, each filter being 3 by 3, you're going to get a final output shape which would look like this. Okay, so what are the dimensions of this output shape? Again, each filter is creating one surface, one 2D shape of 26 by 26. Because we have 10 filters, you're going to have 10 of these 2D surfaces. This is what your convolutional operation is doing. So each filter here is trying to capture different types of patterns in your original input image and basically transform the original input image into more meaningful representations. That's going to help in the final goal of classifying this image as it belonging to like one of the 10 classes, being this image is just a pullover. Okay, and again, the values, right? The values of the filter, for the sake of explaining, right? I have chosen some values here like 1, 0, -1, But in reality, even the values of the filter, we don't have to choose. They are the weights which the algorithm or the network automatically calculates as a training process. So this is the beauty of deep learning. This is the beauty of convolutional layers. Okay, so what we have seen so far is convoluting a 2D grayscale image, right? With 10 filters, you're going to get this output, a 3D output. But what if the image is not grayscale, if it is a color? So let's look at that. So if you have a 3D color image, right? So now, how does our input looks like? Well, our input looks like this, right? So you have 32 by 32 is the 2D shape, right? But it has a depth of 3. If it's a color image, you have RGB, red, green, blue. So this is how your input pixels look like. It's a 3-dimensional shape, 32 by 32 by 3. Okay, so if our input image is 3D, because it's a color image instead of grayscale, right? We have 3 channels here. So how does our filters look like? Well, the filter also now, instead of being a 2-dimensional filter, you're going to have a 3-dimensional filter. So this is automatic. So whatever the input channel depth is, like let's say in this case 3, the filter depth will be the same. So typically when we choose the filter in Keras or in deep learning, we don't even have to specify the depth here, depth of the filter. It automatically, whatever the depth of the input channel, the filter's depth is going to be the same. Okay, so now let's look at the convolutional operations. How do you think the convolutional operation is going to look like? Well, you take this 3D filter. Again, you put it on your original input image, right? Which is now the 3D image. So you put like this, okay? And then you do the convolution. It's still the same. So you do the element-wise multiplication of each element of the filter with the corresponding value in the input, in the 3D input portion of the image, and you sum it up. And when you do that, what are you going to get? You're going to get single value. But as you scroll or slide that's 3D input filter over your 3D input channel, you're going to get new values, right? For each position, you're going to get a value. And as new values means you're going to get eventually a 2D shape. You're going to get a final 2D shape. right? See, as you're scrolling this, 3D filter, right, toward the entire input 3D image, you're going to get new values, and ultimately you're going to create a new 2D shape. So each filter is going to create a new 2D shape. Okay, something like this. Okay, and the output will shrink a little bit. So your original 2D input image was like 32 by 32, but see, now it became 30 by 30. Okay, now instead of one filter, if you use 10 filters, right? Similarly, each filter is going to convolute the original 3D input image and is going to create a new 2D output shape. And because you're using in total 10 filters, you're going to have 10 2D output shapes with the essence that the final shape would look like this, 30 by 30 by 10. Okay, so again, what the convolutional operation is doing is, what these filters are doing is, they are scrolling over your original 3D input image and trying to identify different types of localized patterns, each filter capturing a new different kinds of patterns, okay, at a particular location. And then that's the reason you have 10 filters, each of these filter will capture different pattern. Okay, I don't want to repeat myself too much, which I think I often do, because I want to make sure that everybody understand. Okay, now again, what filter value should we choose? Because to do the element-wise multiplication of the values in the filter and the corresponding portion in the input image, right, we need the values for the filter. So as I explained in the previous slide, we don't have to actually guess them. I mean, we don't give them, right? The algorithm automatically calculates them. Initially, it does guess them. It guesses some weights. And just like, for the dense layer, you guess the weights. So you guess the weights, you do the convolutional operation, you calculate the output shape, you keep going until you get the final, y, and then you compare with the actual y, get the loss, take gradient, update weights. And in this process, these weights are automatically optimized. Once the model is learned, the training process is done, and your cost function goes to 0, these weights are become optimized, and the model is said to be, the network has learned. It was able to fit on whatever the training data you have pretty well. And then if you give it a new color image, it's going to do the job for you. It almost all feels like a magic. Okay, so this is in brief about the convolutional operation. Okay, now we're going to talk about something called padding. So what is padding? So there are a few other concepts. Convolutional operation is the main thing when it comes to convolutional neural networks. Right? Then you have some other additional concepts which we need to know. One of that is padding. So what is padding? First, I'm just going to show you same thing what I did before. I'm going to take a sample, hypothetical 6 by 6 pixels image. I'm going to take a 3 by 3 filter. I'm going to put it there. I'm going to slide. I'm going to do the convolutional operation, right? I'm going to go one window at a time. And as I do that, I get a new final output shape. And let's say this output shape is 4 by 4. Okay. Good, right? So what is the problem here? Well, the way we are doing the convolution right now, right? These corner elements, the corner elements are not getting equal importance. We're not able to do centered convolutions on them. So because the corner elements, if you want the corner elements to get equal importance, then we do something called padding. Padding is just like adding extra, rows and columns of zeros, right? So the only purpose of doing this padding is because if you add the zeros in this fashion, right? If you add this padding, basically you pad it. Now it became, instead of 6 by 6, your original input image became 8 by 8. It doesn't mean anything. You're just adding an extra zeros, okay? But for the convolutional operation, see, now you're going to start here. See, now, this corner element, now you're doing it like a centered convolution. So they're going to get equal importance as your interior pixels. If you want the pixels on the corner regions, on the outer regions to get equal importance as the internal pixels, we typically do the padding. Okay, by adding these zeros. So when you padded it, it became the 6 by 6 image became 8 by 8 pixel, right? So now everything is the same. So now you're just going to take the filter again, you slide one window contiguously, right? As you do this, you can keep scrolling, and then again you're going to get a new output shape now. But your output shape, instead of being 4 by 4, right? Now this will also change. So now this is 6 by 6. See, your original input image was 6 by 6. Now the output also is 6 by 6. Right? But the main reason we typically do padding is because, we want the corner pixels to get equal importance. And also, because as you saw here, the original input image was 6 by 6, output was 4 by 4 without padding. Now with padding, the output image has become, 6 by 6 also. So this is the purpose of padding. Again, we're gonna do padding for many of the hands-on projects later when you are doing the convolutional operations. No, not just convolutional operations, actually, even when we go to NLP. So you can see the concept of it. The concept of padding is pretty much the same. You add these extra zeros. Okay. All right. So there are two types of padding now here. Valid padding and same padding. So valid padding means no padding. I mean, don't get confused when we say valid here. What we mean is like valid windows. So, because the corner pixels doesn't get equal importance, we're adding extra zero. We're creating this like, in essence, we are putting a different kind of window there. So we're saying, no, just use valid window. Whatever the valid windows are, use them. So basically meaning no padding. So remember, valid in Keras, when you say padding is valid, you're basically saying no padding. Okay. And then you have an option of same padding. Same padding means, you put the padding in such a way that your output image is the same as the original input image. So the original input image was 6 by 6. I mean, even though you put zeros and made it 8 by 8, right? In reality, the original input image is 6 by 6. So, and you can see the output after the convolutional operation is also 6 by 6. So if you want that, select padding equal to same. Again, you can do that in Keras or TensorFlow. Okay. All right. So then another concept we need to understand is strides. So what is strides? Again, let's just take a hypothetical image with some hypothetical values for these pixels, input 7 by 7 pixel, let's say, and then let's take a filter. Okay. Again, some sample values are put in the filter just for the sake of explanation. So we're going to convolute this input image with this filter using stride equal to 1. So what is stride equal to 1? You might have already guessed, right? Strides. So as the sliding which we're doing, right? The sliding which we're doing, if you do this contiguously without skipping any column or any row, that is stride is 1. Okay. It's just going very continuously, you're not skipping anything. You're just going contiguously. You're sliding the window. Okay. If you do that, your output shape is going to look something like this, 5 by 5. So that is stride equal to 1. But let's say you increase the stride. What happens? So again, take this same 7 by 7 pixel input image. You start with a 3 by 3 filter. So you start here. See, but now when you're striding, right? When you're sliding, so instead of going contiguously, you're going to skip one column. Did you see? So you're going to skip one column because stride is equal to 2. Similarly, you're going to skip it again. Same thing. So same thing, going to skip a column or a row, and bottom line, what's going to happen is your output shape, instead of 5 by 5, it's going to have only 3 by 3. So typically striding, you want to skip some rows and columns, or you want to downsize the input shape dramatically. Again, you can use strides. Okay. We're going to use padding. We're going to use strides in some of the hands-on projects we do. That again, you can see it more clearly, the effect of the padding and striding. Okay. All right, so let's put all this thing together, the convolutional operation, and see in practice, like let's say, what's going to happen to it, an input image. So let's take again a color input image, okay, 32 by 32 by 3. It's a 3D, input image. So this is our input layer with 3 channels, okay. So let's say we have first convolutional layer, we're going to have 10 filters, okay. Each filter is again 3 by 3. As I said, the depth would be the same as the input channel depth. Okay, so 3 by 3 by 3 filter. Let's say we don't have any padding and stride is 1. Okay, stride is 1 means it slides, each of these filters slides the 3D input image contiguously. All right, it's not gonna skip any row or column, and there is no padding. If that is the case, again, each filter as it convolutes the input 3D image, it's going to create a output shape, a 2D output shape. Okay. Now, because we have 10 filters, we're going to have 10 2D output shape, which is nothing but a 3D, right, output shape, and it's going to look like that. So the 2D shape has shrunk a little bit from 32. It became 30 by 30, but because of 10 filters, you have the depth of 10. Okay. So this is your convolutional layer 1. Okay. On top of this, let's say we do another convolutional operation. So now with 20 filters, okay. So again, each of my filter now, its shape will be 3 by 3, but the depth will be 10. As I said, the depth of the filter is the same as the depth of the input channel. Okay. Now let's, for the sake of explanation here, I want to show you no padding and padding. So padding, let's say now same padding. So we are gonna use some padding, but let's say same padding. And strides equal to 2. See, if the strides was not there and padding equal to same, the output shape would look the same as the input shape. But because you were using strides equal to 2, your output shape will actually shrink, even though you're saying padding equal to same. Because see, previously I said use padding equal to same if you want the output shape the same as the input shape. But the moment you have strides equal to 2, your output here is going to shrink again. But I just want to just explain to you. So now, again, each filter, each 3 by 3 by 10 filter is going to convolute this output of the first convolutional operation, the 30 by 30 by 10, right? And it's going to create a 2D shape. Because you have 20 filters, the depth now is going to be 20. And the new output shape is going to be like this, 15 by 15 by 20. And this is your convolutional layer 2. Okay? And then the output of the convolutional layer 2, right, this 15 by 15 by 20, we're going to flatten this one. Why do we flatten this? Because our final layer, the final classification layer, the output layer, the Vipred layer, that's going to be a dense layer. Because that's going to be a dense layer, right? This final layer is going to be a dense layer with 10 classes, 10 units. We want the input to the final dense layer, the Vipred, to be flat. It needs to be like a 1D. Flattened one. So we flatten this 15 by 15 by 20. So there is a typo here. Let me correct this. And then you initialize the weights, right? So this is the skeleton of the neural network, right? So this is what, just to show you what kind of layers we have. So we have a convolutional layer, right, which modifies your 3D input layer into a 30 by 30 by 10 output shape. Then you have a second convolutional layer, right, which is going to transform your input of 30 by 30 by 10 into a 15 by 15 by 20 output shape. And then we're going to flatten this 15 by 15 by 20 shape into a flattened layer. And then on top of this, we're going to use this to calculate the final output layer, the Vipred layer. This is the skeleton. But the actual process starts with by initializing weights. Let's say the pink weights or the weights belonging to the first set of filters, this 3 by 3 by 3 filters. So you're going to populate this with, the weights. Basically, the network guesses these weights at the first step, and then you guess the weights of this 3 by 3 by 10. These 20 filters you are seeing in blue, you're going to guess those weights, right? And then you're also going to guess the weights here, because this is the densely connected layer between the Vipred and the flattened layer. So you're going to guess some weights here too. So guess all these weights. And once you have the weights, you can calculate the first output shape of the first convolutional layer, output shape of the second convolutional layer, and the flattened layer, and the final output layer. And then you compare the Vipred with the actual Y, get the loss, sum the loss over all the images, get the cost function, take the gradient, remember, and use that gradient to update the weights, iterate the process, continue until your cost goes to 0, and your algorithm has learned, it has become smarter. And if you give it a new color image, it's going to classify whatever the classes, whatever the output classes we want it to be classified into. So this is the magic of convolutional operation. Now, if you're wondering, how do you calculate these output shapes after each convolutional, the 32 by the first convolutional operation, right? After that, the 32 by 32 by 3 input image has become 30 by 30 by 10. And for the second operation, the 30 by 30 by 10 became 15 by 15 by 20. I mean, is there a formula? Yes, we can simply use this formulas here. Again, if you want to double check your understanding, you can play with different kind of input shapes and padding and the strides, and use these formulas, which can tell you. For example, in this case, for the first convolutional operation, so input height, let's say 32 minus 3 is 29, stride is 1, no padding, right? So 32 minus 3, 29, 29 plus 1, 30. So 30 comma 30, and number of filters is 10, so you have 10. Right. Similarly, for the second convolutional operation, the padding is same, because we're saying padding is same and strides is 2. So you're going to use this formula. So what is the input height? 30. So 30, what is the stride? 2. 30 by 2 is 15. 15 comma 15 comma number of filters. So number of filters is 20. 15 comma 15 comma 20. Okay. So this is what, convolutional operation is about. Hopefully, by putting everything together, you can see. Hopefully, this gave you a better insight. Again, for any of you who are completely new, to convolutional operation, ever heard about them before, or even maybe some of you might have heard about convolutional operations, but never really got that complete gist or complete intuition. Hopefully, this video is helping you. All right, we have seen how convolutions actually extract features from images. In the next video, we'll add one final core building block called pooling layers. And we'll see how everything comes together inside a full CNN network or CNN block. This lesson is again part of my deep learning mastery course on Udemy, where I go step by step from intuition to hands-on projects. I have linked the full course below if you want to follow a structured path. All right. We have seen how convolutions actually extract features from images. In the next video, we'll add the final core building block, pooling layers, and see how everything comes together inside a full CNN block. This lesson is again part of my deep learning mastery course on Udemy, where I go step by step from intuition to the hands-on projects. I have linked the full course below if you want the full structured path. And again, thank you so much for watching this video, and happy learning, and let's continue. All right, we have seen how convolutions actually extract features from images, how they create the feature maps, right, going from simple 2D or 3D images. In the next video, all right, we have seen how convolutions actually extract features or feature maps from images, going from this 2D or 3D images to the final output shapes or the feature maps. In the next video, we'll add the final core building block, pooling layers, and see how everything comes together inside a full CNN block. This lesson is again part of my deep learning mastery course on Udemy, where I go step by step from intuition to hands-on projects. Again, if you're one of those structured learners, I strongly recommend check out that link. I have linked the course below if you want to follow the full structured path. Thank you so much for watching. Happy learning, and I will see you in the next video.